So welcome back to our notes for writing polynomial equations. And before we get started with example 3, I'd like to look through this set of problems here where we're given a polynomial f of x, and we're not going to write the equation of this polynomial. Instead, we're going to apply the fundamental theorem of algebra and transformations to see what kind of things we can do to change what type of zeros that we have from this function. So if this is my polynomial, this red graph f of x, and I want to use vertical transformations with that polynomial to write an equation where the graph has real zeros. Okay, right now it has 1, 2 crosses and a bounce, right? So there's a 0 at x equals -2, x equals 0, and x equals 2. That's 3 distinct real zeros, one of them with multiplicity of 2, right? I want to do a transformation to this graph so that it has 4 real zeros. And to make that happen, I would need to move this function up. So for example, if I move this polynomial up enough that now it has 1, 2, 3, 4 crosses, right? It would then have 4 distinct real zeros. So I would need to take my polynomial f of x, and I would have to add a constant to it. So I'm going to go ahead and call that constant c. So I'm going to add a number c, but I can't just add any number c, because if I go up too far, right, if I were to go up, say, 6, then it wouldn't touch the axis at all. So I'm limited in what the c can be so that it would have 4 distinct real zeros. So my c, if I move up 1 unit, that would work, right? But what about 1/2 or 1/3? Right? Any movement up more than 0 is going to produce 4 distinct real zeros. So my lower bound for c would need to be 0, right? Less than c, less than. And then my upper bound, if I move this graph up 1, 2, 3, 4 units, then I would have 2 bounces on the x-axis. That wouldn't be 4 distinct real zeros anymore. It would be 2 with multiplicity 2. So in order to get my 4 distinct real zeros, I need to be between 0 and 4, non-inclusive in my translation. Okay, so now I'm going to look for 2 real zeros, each with multiplicity 2. And I know that to have multiplicity 2 means that there would have to be bounces on the x-axis. So I would start with my polynomial f of x, which is shown in the graph, and then I'm going to add a constant c. The c that I add is going to need to be an exact value, right, in order to get these two turning points, these absolute minimums, to sit right on the x-axis, right? That would be 2 bounces then, which would be 2 real zeros, each with multiplicity of 2. So as I sketch that, I would need to come down, bounce, right, bend, and then bounce again off of the x-axis to have those 2 real zeros, those 2 distinct zeros, each with multiplicity of 2. So to make that happen, my c is going to have to be 1, 2, 3, 4. So c is equal to exactly 4, right? It can't be anything other than 4, or I would not have the bounces right on the x-axis. Okay, next I want to find 2 real and 2 imaginary zeros, and this is where we get up here to this this fundamental theorem of algebra, where all polynomials have the same number of complex zeros, real and imaginary, as its degree. Multiplicity is included in that. So here I had 4 real zeros, so that's my degree 4 polynomial. Here I have 2 real zeros, but that multiplicity of 2 still brings me to a total of 4. So the fundamental theorem of algebra still holds. Now if I have 2 real and 2 imaginary, that 2 plus 2 is still 4, real zeros, but it's only going to cross the axis at x-intercepts 2 times in order for 2 of those to become imaginary zeros. And that would happen not by going up, but by going down, right? If I move this polynomial down c units, now I'm going to have 2 distinct real zeros, and they're crosses, so they have no multiplicity. But because of the fundamental theorem of algebra, I know my degree still has to be 4, and 2 real with no multiplicity isn't 4. So by sliding it down, I now know that I have created 2 imaginary zeros in my graph. So f of x, right, we're doing vertical transformations. So I've got my f of x plus c, and now I want my c to be negative because I'm going to move this entire function down. So my c is going to need to be less than 0, right? So if c is 0, I'm here with my 2 crosses and 1 bounce, right? So that would still be degree 4. 1 plus 1 plus 2 is 4. But if I move it down even a little bit, so down a third or down a quarter or down an eighth, now that bounce is no longer at the origin, it's below the origin. And so that's how I get these 2 crosses and 2 imaginary zeros. Okay. Now there's no limit because of the end behavior, because these ends are both approaching positive infinity. There's no limit on how low I can go, right? There's just an upper bound where I cannot use 0 or anything higher and produce that graph. Okay, last but not least, we want 4 imaginary zeros, and that means that no part of this function can touch the x-axis. So I would need the entire graph to be up above the x-axis to have 4 imaginary zeros, right? And I would still be adhering to the fundamental theorem of algebra. There'd just be no real zeros because it won't touch the axis, and all of our imaginary zeros would total 4. So that will happen by starting with my function f of x. We need a vertical translation, so plus c, and in order to get my graph to be up above the axis, I'm going to need to be greater than 1, 2, 3, 4. So my c must be strictly greater than 4, right? If it was exactly 4, then I would be back here with 2 bounces. If it was between 0 and 4, I'd be up here with 4 distinct real zeros. But if it's greater than 4, then I have 4 imaginary zeros. Okay, so now that we've looked at a review of imaginary zeros, we can go ahead and try example 3 together. So we've got a leading coefficient of 1, zeros of x equals -2, and we see that's a cross at -2, so that's going to be a single root, x equals -2. Okay, then at 5, there's another cross, so that's also a single root, x equals 5. And then we have 2 imaginary zeros, plus and minus I. And when we look at the graph, right, we can see that there's only 2 real zeros at -2 and 5, but we do have some bending, some turning going on here, and that accounts for those imaginary zeros. If I were to raise this function up like we did in that last example, you can see where this bend here would touch or could touch the x-axis, and then we would have a bounce, right? If we moved it up just a little more, we'd have 4 distinct real zeros. So this is going to be a degree 4 polynomial, but in its current state, 2 of those zeros are imaginary. So x equals I and x equals -I, right? Those would be our remaining 2 zeros. So step 2, we want to write that polynomial now in factored form, and it said the leading coefficient was 1. So we have y equals x plus 2, that's our factor that corresponds to the 0 of x equals negative 2. Then we'll have a factor of x minus 5 corresponding to our 0 of x equals 5. We'll have a factor of x minus I corresponding to our 0 x equals I, and then a factor of x plus I corresponding to its conjugate, negative I. Okay, now to write that equation in standard form, I'm going to FOIL this binomial x plus 2 with the one beside it, x minus 5. So first outer inner last, x times x is x squared. Then x times negative 5 is a negative 5x. Then I've got my x times 2 is plus 2x. So negative 5 plus 2 combines to be negative 3x in the middle. And our constant 2 times negative 5 is negative 10. So that would be my product of these two binomials. Okay, then I'm going to look at my x plus I, x minus I factors. Those are a difference of squares. And I can use difference of squares shortcut then to square the first. X times x is x squared. Then I'd have a minus and I'd square the last. I times I is I squared. But remember, I squared is negative 1. So I squared, x squared minus I squared is actually x squared plus 1, because minus a negative is a positive. And now we can go ahead and expand by doing repeated distribution. So we're going to distribute x squared times x squared, and that is x to the 4th. And then we have x squared times 1 is a plus x squared. Then negative 3x times x squared is negative 3x to the 3rd. Negative 3x times 1 is a minus 3x. And then our constant, negative 10 times x squared, is negative 10x squared. And negative 10 times 1 is minus 10. So in our last step to put this into standard form, we just need to combine like terms and rewrite this in order of decreasing exponents. So we've got x to the 4th as our first term, and then negative 3x to the 3rd power. That's our cubic term. Okay, then we have an x squared and a negative 10x squared. Those are like terms, so we're going to combine those like terms and get a negative 9x squared for the quadratic term. Okay, then we have minus 3x. That's our linear term. And then the constant down here at the end is a negative 10. And that would be our polynomial of least degree that has a leading coefficient of 1 and zeros of negative 2, 5, and plus or minus I.